Hi, thanks for coming today. As Sandeep mentioned, I'm a developer advocate for Databricks, and today's talk is the incremental ETL architecture. We will pretty much focus on open source technologies around Apache Spark and Delta Lake, both of which are championed and pioneered by Databricks. Just a little bit about myself. I'm John O'Dwyer, developer advocate. Before joining the Databricks team as a developer advocate, I was a solutions architect here for 4 years. And before that, I was a data scientist and a developer, early adopter of both Apache Spark and also the platform of Databricks. Outside of work, I live in Denver, Colorado. I try to get up to the mountains and enjoy outside activities in the mountains with my family. So, excuse me, one sec. Very sorry about that. All right, the incremental ETL architecture. It actually really starts with ingest, and essentially what we're trying to do is only move data between source and destination, and multiple sources and destinations, but only moving the data that is either new or changed. This is an idea that really isn't very new. It actually is something that data warehousing and ETL can do, but the ability to do it at scale in big data environments is actually something new, and really is spearheaded by innovations that Delta Lake and also Spark as a whole help with. Why? What are the advantages? And these advantages are directly related to big data. Big data storage is inexpensive. It also it separates storage from compute. What that allows you to do is, instead of actually holding information in memory, for example, in certain cases, or anything that's like hot swappable, it allows you to store the data completely separate from compute, so that it's extremely cheaper to actually keep that in storage and not worry about the computation that is involved with accessing that data. It's also you can also retain all history, which comes in very handy in a lot of cases. For example, we have a Fortune 5 company that uses our technology and Delta and structured streaming to essentially keep years worth of logs for threat detection. And the reason why they use this particular type of architecture is so that they can keep all history instead of only keeping, say, 90 or 30 days worth of information, so they can do threat analysis over the course of years. It's also efficient. The reason is quite simply, you're only processing new or updated data, as opposed to reprocessing information that ancillarily needs to be changed in an object store. Let's say you have an object that actually holds thousands of records, and you only need to change one. In times past, you actually needed to essentially, this is simplifying it a little bit, but you would need to blow away that whole file, or maybe even a whole partition, and change that whole set and then update the values. And the whole time that you're doing that, you couldn't have other people hit the information at the same time. That was very inefficient. The other thing that's great as an advantage is that you can actually have these as multiple data sets. For example, this bronze, silver, and gold architecture, it looks linear, but it doesn't necessarily have to be, and the end results can be different. There's generally speaking, these gold tables are either for aggregated data sets that are used for business intelligence and analytics, or feature sets that are used for machine learning, whether it be training models or inference after the training is done. And this isn't necessarily usually linear. You would have almost a DAG of bronze, silver, and gold tables over the course of everything. Other things that make this advantageous, these tables can be are atomic and always available, as I had mentioned before. It used to be very inefficient if a value needed to change and only one value in a table needed to be changed. Sometimes you'd have to blow away that whole set. The transfer of the data is also stateful, and you can and we will get into how this is stateful, but essentially we keep track, we being structured streaming keeps track of where the state is at any given time, and that includes stopping for jobs or errors or the like. And in the case of latency, you can actually change the cadence of these runs. Structured streaming, Apache Spark structured streaming specifically, is made to be continuous, so 24/7 and extremely low latency, so that essentially information can be picked up right away and move through the system. But at the same time, and we will get into how to do this, they can also, those same jobs can be changed from continuously streaming to scheduled, using something called trigger once, where instead of just running continuously, you can let the system identify when it's done with the information or processing the data that's associated, and it will cut itself off. And then you can actually run these on a schedule, say daily, monthly, hourly. And the really nice part of that is you can actually drop the cadence over time, so that it can be continual if you like. Since storage and compute is also separated, you can essentially keep historical data sets. There is also the ability to version, and Delta Lake tables are versioned, and you can always go back to historical data sets and reproduce things like specific ML models directly from the old data sets as they were historically. So why is this hard now? Well, the reason is that, and it's not necessarily just now, these technologies like Data Lake, Delta Lake are actually have been around for a little while, but preceding them, the only way to really do incremental ETL was through warehousing, data warehousing, where you can actually on a row by row basis pick and choose what needs to be changed, but that is expensive. A lot of data warehouses also do not separate compute and storage. Updating data in big data was not necessarily possible, and state is hard to keep track of. There's a term called idempotency, and essentially that's a big word for pick up where you left off. So essentially, this state will actually do exactly that, where if something errors out, if something has finished and needs to restart, instead of keeping track of where you left off or recomputing old data that may or may not have actually gotten in, and then dealing with whether that information is duplicative or if it needs to be reevaluated. Essentially, structured streaming takes care of that by like just out of the box. And then also, you're only computing what rows have changed, and that's instead of the inefficient manner of doing everything and trying to understand what has changed and what hasn't. So before going on, I just wanted to see if Sandeep, if there were any questions, I can take those. If not, we can actually save a little time at the end for a little demo. But if there are any questions that you think that we should answer, let me know.
Yeah, no questions. You're free to continue, sir.
Okay, great. Thank you. So let's step through the different pieces of incremental ETL. And starting from left to right, well, actually starting on the left is ingest. And this is actually the piece that generally is outside of Apache Spark structured streaming and also Delta Lake. And it's around streaming ingest or queue-based ingest. These are continuous or scheduled ingest. The difference is, again, based off of if you want to identify when something is finished and for the stream to shut itself down or not. And we'll talk about the functionality of what that looks like in a bit. Popular modes of ingest are Kafka. That would probably be the main open source technology that people use for this. Others are Kinesis on AWS, Event Hubs on Azure, and then queue-based systems would be SQS, which is on AWS. Databricks has a technology called Autoloader that's great for this. In the case of Autoloader, you can actually drop values directly into object storage on the major cloud providers, and it will identify identify in order which data needs to be evaluated first. And the use of autoloader actually removes the need for an extra layer of technology and functionality for streaming. So as I mentioned, there's two main components to incremental ETL. Those are Apache structured streaming, which we'll discuss here, and the attributes of it that lends itself to incremental ETL. The other being Delta Lake, and we will discuss the features that we use in incremental ETL in a second as well. I had mentioned the term idempotency. That is directly related to the checkpoints in state and how it's saved. In this green part here, it's actually the bottom This second line of the green is where you specify a checkpoint location. And that will automatically actually save where you've stopped writing at. I'll explain this as well. What we're doing in these two lines, you actually have a read stream and a write stream. So the read stream actually reads from a place. In this case, it's reading from a format called cloud files, which is the autoloader format, into a streaming data frame. And then the write stream writes it out, in the case here, into a delta table. So this would actually be writing from ingest to a bronze table. And using this checkpoint location, essentially as it's writing the metadata that's associated to the state of where it is at any given time, what that allows it to do is when the stream identifies that it's finished reading data, it can shut itself down, and that checkpoint location will understand where to pick up when the next run needs to happen. This is actually great for errors as well. As we all know, there are foreseen and unforeseen exceptions and errors that happen in data ETL, and you know, these types of architectures this is no exception, and this helps in that case. The other part of structured streaming that is very great in incremental ETL is the ability to go between continuous and scheduled, in this case ingest, but we will talk about continuous and scheduled traversing of data between delta tables as well. And how you do that is the use of trigger once. Trigger once is the first green line here. You don't have to put this in. If you don't, this combination of a read stream and write stream will be continuous, and it will just continue to go, and it won't identify to shut itself down. Totally fine for applications that need to run 24/7. Many and most do, but a lot of the times what happens is a lot of people want to be able to do this in a schedule because there's two reasons. You might want to either you might not have enough data to continually run, or you may want to not be burdened with a continuously on 24/7 stream, where you could actually identify and administer it a lot easier if it shuts itself off. One of the main reasons why Delta Lake is a great big data table for incremental ETL is literally the ability to update, delete rows in a table. This really wasn't possible before on big data object stores. Delta Lake makes it possible. There's a lot of back and forth and reasons how this happens. You've probably seen other presentations on the inner workings of Delta Lake, and there definitely are. But for this conversation, really just going to keep it high level. One thing that I did want to point out here is specifically the merge into statement, because update and delete statements, those are pretty standard, and you've probably seen those before. A merge into statement may not be quite as familiar. These merge statements, or sometimes they're called upsert statements, they make it possible to, in a very concise way, delete, update, or insert all at the same time given one table. This comes in handy when doing incremental ETL using structured streaming. I will show you an example of this actually later if we still have time. So the other thing that that Delta Lake, the features that allow Delta Lake to be great for incremental ETL of big data at massive scale is the movement itself. Mostly that it can be a streaming source and sink. So in the case of moving data from a bronze Delta table to a silver Delta table, both the in that case, both the source of that stream and also the sink, which is the silver table, are both Delta tables, and there is no need for other types of streaming technologies to be in between them. It actually makes it a lot more seamless and easy to deal with. This is also built into the ACID transaction nature of these tables. That being that as you have outside sources or outside consumers of these tables, they can actually read these tables in real time and get the most up-to-date versions of those tables based off of the ACID transactions. And those transactions also make sure that none of the data is corrupted at any given time. The other thing that actually really helps here is that the Delta tables do have a schema that is enforced and also can evolve at the same time. What I mean by that is, let's say you have a bronze table that has 5 columns, and your ingest is given a 5th column that is outside of the initial schema. You can determine if you want to enforce that schema and what you want to do with that new column. You can the default's actually just to append it if you are allowing for schema evolution. There's other various cases as well. You can even fail if you see data that you hadn't seen before, then reevaluate if you want to actually include that data. It makes it very flexible. This flexibility is really key to the business outcomes. Reason being is that you can allow new data to come in and evaluate what that new data is without corrupting the column sets and the schema in a way that wasn't really possible before. Parquet, at its core, it's a great technology that allows you to actually evolve, but these schemas, in the case of Parquet, they can evolve in ways that will corrupt the data because they are atomic to a field instead of holistically looking at the whole table. So that's the end of my presentation. We do have a couple minutes. I will be available in 5 minutes in the Q&A section. But I did want to, since we did have a minute or two, I did want to go into the incremental, into an example of incremental ETL. Specifically, I wanted to actually show you how data can be added and updated at the same time in a streaming manner, and how to identify the changes based off of that. This is a clearly you would be dealing with much larger data sets. In this case, we are going to include a set of 6 rows and then another set of 6 rows. The first set of 6 rows are earnings per share. Earnings per share or estimated earnings per share by analyst for March 1st, 2021. I'm going to skip down to the secondary set that I'm going to include, and it's going to include all of the estimated earnings per share by analyst for these stocks for April. But as you can see, there's one row that's actually updated a value for March. So we have to figure out how we can accept that information into the bronze table and also then progress it into a silver table that is that's clean, and then can therefore actually go downstream and be updated even further if needed. So, which is a very powerful idea. Think about it in this way: like if in one, things need to be updated. That's one problem. But two, even past that, models change. Feature sets of models, in the case of machine learning, those also need to be changed and updated over the course of time. If you can update these values instead of blowing away a whole set, and also do that in an incremental fashion so that it actually daisy chains all the way through your ETL, that is going to be a lot more seamless, a lot more efficient, and also really really open up architectures that weren't possible before. For example, having multiple different types of gold tables at any given time, and also the ability to update those gold tables in real time. So as we can see, we have one extra row. This is essentially what we saw before with the read stream from autoloader, and then to a write stream. We're actually doing this in trigger once. And as we can see in here, in the bronze set, we actually have two different values for earnings per share for analyst 2 on stock A. So this 2.4 is a new value, and this is the old value that we are actually replacing. So what we can do, and I know I got 2 minutes, I'm going to show this real quick and then we can actually jump out. What we can do is, I'll come back up to the upsert to delta, but as you can see here, we have a read stream. We drop the rescue data column from the bronze table, and then we're writing that silver table into the silver table, but we're actually going to go through for each batch. This for each batch function is where all the magic happens. And this is iteratively identifying in that new table, based off of that micro batch, what values in that micro batch need to be merged into that table, whether it is, in this case, an update or an insert. We don't have a delete case here in this use case, but in this case, we're in real time and streaming, updating a Delta Lake table using a merge statement. And that's what I wanted to show you today. Thank you very much. If you have any questions, I will be in the Q&A section of Spatial Chat, and happy to discuss any of this or anything else that you really want to talk about, to tell you the truth. Thank you.